Hi everyone. Today I am going to explain about analog and digital electronics. I am Dr. B. Ravi Kumar, Associate Professor, Department of ECE, Institute of Aeronautical Engineering. Before going to start my lesson, actually this analog and digital electronics having two parts, analog electronics parts and digital electronic parts. Analog electronic parts which covers the operation of the p-n junction diode and its characteristics and its applications. An operation of bipolar junction transistor and its characteristics and its applications. And the second part, digital electronics, which covers Boolean algebra and optimization of Boolean functions using K-map and tabular method, and then design combinational circuits and design of sequential circuits. Let us see the first part, analog electronics. In this part, the students should be able to understand the fundamental knowledge of the semiconductors, devices, and p-n junction diode, its characteristics. Basically, materials are broadly classified as conductors, insulators, and semiconductors. Conductors have rich conductivity, and insulators have poor conductivity, whereas semiconductors have electrical property of conductivity lies between insulator and semiconductors. The best examples of semiconductors are silicon and germanium, and these semiconductors like some diode and transistors and solar cells and light emitting diodes, etc. We can classify these materials by using energy band diagram. What is energy band diagram? Energy band diagram is a collection of energy levels which describe the valency band and the conduction band. The all energy levels initially which are in the valency band, whenever the electrons which are in the atoms are excited, then the electrons which gain energy to move from valency band to conduction band. So based on this energy band diagram, we can distinguish between insulator, semiconductors, and conductors. First, we will see that insulator. So initially, in the insulator, all valence electrons are which are in valency band. So the energy gap is more in insulator, which is equal to or greater than 5 electron volts. So because of this large energy gap, so whenever electrons are excited, but they are unable to move from valency band to conduction band. That's why all insulators have poor conductivity. Like for example, wood, mica, eraser. And when come to the conductor, in this conductor, the covalent bond, valency band and the conduction band both are overlapped. When both are overlapped, there will be no energy gap. Immediately after giving excitation of electrons, then they are moved from valency band to conduction band. That's why conductors have poor rich conductivity. Coming to these semiconductors, in this semiconductor, there will be a less energy gap between valency band to conduction band. For example, energy gap for silicon is 1.1 electron volt, and energy gap for germanium 0.67 electron volts at room temperature. So based on energy gap, we can divide that insulators and semiconductors and conductors. But in this subject, we are going to use those semiconductors materials like germanium, silicons used in electronic devices like diodes, transistors, and LED, etc. First, we will see that classification of semiconductors. There are intrinsic semiconductors and extrinsic semiconductors. First, we will see that intrinsic semiconductors. By using the atomic structure, we will see that what is the intrinsic semiconductors. In this figure, there are two atomic structure. Figure A represents the germanium and figure B represents the silicon. We know that germanium, the atomic number is 32, and silicon, the atomic number is 14. In both cases, the valence electrons are 4. We will write this, for example, for take silicon, we will write using Schrodinger equation 1s2, 2s2, 2p6, 3s2, 3p2. So in this, the first orbital having 2 electrons and the second orbital occupies 8 electrons and last orbital occupies 4 electrons, which are also called valence electrons. In this atomic structure, this is nucleus. It is a center of the atom, and all electrons which are in the orbital revolve around the nucleus. So these are called valence electrons. Similarly, for germanium, based on its atomic structure 32, they occupy different electrons in different orbits, but in outermost orbit having 4 valence electrons. If you see the covalent bonding of these semiconductor materials, for example, this is the atomic structure for silicon. So in this, the circle with the Si, which represents the atom. Remember, students, all inner orbits of electrons are not shown in this figure. Only that valence electrons have shown in this figure. So which represents with a circle with this silicon represents the atom of silicon atom, and this 4 minus symbol represents the valence electrons. One atom of silicon is covalent bond with the neighboring silicon atom. This is called covalent bond. In either side of this silicon atom, all 4 valence electrons are covalent bond with the neighboring silicon atom. This can be repeated for entire the 2-dimensional structure for atomic structure by using covalent bond. Now, coming to the extrinsic semiconductors. How to get extrinsic semiconductor from intrinsic semiconductor, and what is the purpose to go for extrinsic semiconductor? So the main purpose to go for extrinsic semiconductors to improve the conductivity, and also how to get this extrinsic semiconductor by the process of doping. So what is doping? It is a process of adding impurities to pure semiconductors. Pure semiconductor is also called intrinsic semiconductor. So we need to add impurities that may be either trivalent atoms or pentavalent atoms of impurities. A semiconductor material that has been subject to the doping process is called an extrinsic material. There are 2 types of extrinsic semiconductors, which are called p-type and n-type semiconductors. Now we will see that how to form p-type semiconductor, how to form n-type semiconductors. Here in this figure, let us see figure A, how to form p-type semiconductors. Basically, it is a silicon atomic two-dimensional structure. All are silicon atoms. Suppose if you take trivalent atoms, which are called boron. So if you take the trivalent atom and replaced with this silicon atom, then we know that boron has 3 valence electrons because it is said to be trivalent. So among these 3 valence electrons, covalent bond with the neighboring silicon atoms. For example, if you see here, this valence electrons, this valence electron, this valence electron, they are covalent bond with the neighboring silicon atoms. Covalent bond with the neighboring silicon atom. Whenever covalent bond with the neighboring silicon atom, there will be a vacant space here. This vacant space is called hole. Whenever we can add more number of boron atoms to the intrinsic semiconductor or pure semiconductors, then the number of holes will be increases. That coming to the n-type material, similarly take the silicon two-dimensional atomic structure and add impurity atoms like pentavalent atoms. Pentavalent atoms like phosphorus, antimony. Like if you take antimony impurities, which has 5 valence electrons, so this is antimony. It has 5 valence electrons. And 4 valence electrons and 1 valence electron is loosely bonded with the antimony impurities. So among these 5 valence electrons, 4 valence electrons are covalent bond with the neighboring silicon atoms, as shown in the figure. But what about the 5th valence electron? The 5th valence electrons are loosely bonded with this antimony atom. This process is continued for with some ratio. Then the number of valence electrons, excess electrons or 5th electrons are increases, so that in n-type material, more number of valence electrons or excess electrons, whereas in p-type material, more number of holes. Because of that, in n-type material, the electrons are called majority carriers and holes are minority carriers. Whereas in p-type material, the holes are majority carriers and the electrons are minority carriers. This is the n-type material and p-type material substrate. If you see that n-type material, that minus symbol represents the majority carriers are called electrons, and the plus symbol represents the minority carriers are called holes, and plus with the circle nothing but donor ions in p-type in n-type material. Whereas in p-type, the minus with circle like this one, which represents acceptor ions, and a plus symbol which represents the majority carriers are holes in p-type, and minus symbol represents the electrons, which are called minority carriers. Now let us see how to form p-n junction diode. We have a p-type material, we have a n-type material. When we take n-type and p-type material combining together, close together, then we will get the p-n junction diode. The operation of the p-n junction diode can be explained with three conditions, which are called zero bias condition, and forward bias condition, and reverse bias condition. First, we will see that zero bias condition. Under zero bias condition, no external voltage is applied to the p-n junction diode. Therefore, the electrons diffuse to the p side, and similarly, holes diffuse towards to the n side through the junction, and then combining with each other, which is also called recombination. Why it's happen without giving any voltage, without giving any potential or biasing to the p-n junction diode? These charge carriers move together because concentration gradient. What is concentration gradient? For example, if you take the p-n junction, this is a p-n junction. We take p-type material and n-type material, combine it together, we will achieve p-n diode. It is a two-terminal device. Initially, p and n are electrically neutral. Under electrically neutral or equilibrium condition, so all ions on p side and n side are equal. So, but in p-type material, we have a majority charge carriers of holes and minority charge carriers of electrons. In n-type material, we have a majority carriers of electrons and minority carriers of holes. If you see this figure, this can be represented this way. So here, this plus with a circle represented on n side can be represented with the donor ions, and p side minus with circle represents the acceptor ions. Acceptor ion with the majority carriers of holes. We know that how these holes represented in atomic structure. So let us take 9 holes are there in p-type, and 9 electrons are there in n-type, which are called majority carriers. Same way, similarly, p-type has minority carriers of electrons. Let us take 2, and on the n side, minority carriers of holes 2. So if you see this figure, how many number of majority carriers are there on p side? 9. Coming to the n side, these majority carriers of holes on p side 9 and holes on n side 2. Similarly, the majority carriers of electrons which are in n side 9 and p side electrons only 2. So this is what concentration gradient. Concentration gradients means the more number of charge carriers are on one side than the other side. The number of charge carriers more on one side than the other side. So due to this, there will be a concentration gradient. Due to this, these charge carriers have a tendency to move from higher concentration to lower concentration. Here also, there will be 9 electrons and 2 electrons. Due to this concentration gradient, electrons have a tendency to move from n side to p side. So that's why in zero bias condition, without giving any potential external voltage, due to this concentration gradient, the electrons diffuse towards the p side. Similarly, holes diffuse towards to the n side through the junction, and then recombination takes place at the junction. When recombination takes place, what happens? This hole combined with this electron, this hole combined with this electron, this hole combined with this electron. When recombination takes place, the hole filled with electron, this negative ion receive one electron, it will become as a negative ion, and a positive with circle on n side donate one electron, then it will become as a positive ion, so that the resultant figure will be like this: negative, positive ions, so here remaining will be same. So whenever negative on p side accept 3 electrons, then there will be form a 3 acceptor ions, and then on p n side there is form positive ion. Okay, if is again they have a tendency, again there will be a concentration gradient, again they have a tendency to move from higher concentration to lower concentration, but due to a negative potential or negative ion or negative charge developed across the p side and positive charge developed across the n side, these negative potential or negative voltage stop the further recombination, or this negative charge stop the further moving of electrons from n side to the p side, and this positive ion on n side stop the further moving of holes from p side to n side, so that this potential across the junction will stop further recombination or further crossing of these charge carriers, so that a voltage developed across the junction, which is approximately equal to 0.3 for germanium p-n junction diode and 0.7 for silicon p-n junction diode. Because of charge carriers depleted across the junction, then that's why this is called depletion width or depletion region. Now we will go for forward bias. First of all, what is forward bias and what is forward bias connection? Whenever a positive terminal of the battery is connected to the p-type and negative terminal of the battery is connected to the n-type, then it is said to be forward bias connection. In this forward bias connection, electrons from n region cross the junction and enter into the p region. Due to attractive force that is generated in the p region, electrons are attracted and move towards the positive terminal. Simultaneously, the holes are attracted to the negative terminal of the battery. So simply we can say that in forward bias connection, majority charge carriers move away from the terminal of the battery and cross the junction, and minority charge carriers are attracted towards to the battery. If you see this figure, so p side having white color majority carriers of holes, and n side black dots of electrons. They are repelled by the plus and minus of the battery and then cross the junction. When they are cross the junction, then recombination takes place and then current flow in the p-n junction diode. The current flow in the p-n junction diode can be represented with the electron flow. Electrons are moved from n side to p side. Then the current direction always opposite to the electron direction. So in this forward bias connection, due to this positive polarity, majority charge carriers of holes move towards to the p side to n side, and majority carriers of electrons in n side move towards from n side to p side, so that the current flow in the p-n junction diode. So that in a forward bias, diode act as a short circuit. This is its p-n junction diode forward bias VI characteristics. In x-axis, we take the forward voltage. In y-axis, we take forward current IF in milliampere. Now, we already know that open terminal p-n junction diode have initially a potential across the junction, which is approximately equal to 0.3 for silicon, germanium, and 0.7 for silicon. In this case, let us take a silicon p-n junction diode. So its cut-in voltage or its existed potential across the junction is 0.7. So whenever we are giving external voltage or varying the external voltage up to this cut-in voltage or up to this 0.7 voltage, there will be no progress in charge carriers moving across the junction. So that is what here in this graph. So for giving 0.1 volts, 0.2 volts, 0.3 volts, there will be no significant change in the current flow in p-n junction diode, because already junction having a opposite polarities of voltage which is equal to 0.7. So when we are giving greater than that 0.7, then only the current will start in the p-n junction diode. So this 0.7 here is called cut-in voltage. Cut-in voltage is the minimum voltage to establish the current flow in the p-n junction diode. So when we given more than this cut-in voltage, 0.8, 0.9, 1, 2, 3, 4, likewise when we increasing the voltage, then greater than the cut-in voltage, then the current flow in the p-n junction diode is exponentially increases. When goes on increases, then the current flow is increases. This is called p-n junction diode in forward bias. Coming to the p-n junction diode in reverse bias, when it is said to be a p-n junction diode is reverse bias, whenever a negative polarity of the battery is connected to the p-type and positive terminal of the battery is connected to the n-type, then it is said to be reverse bias connection. In reverse bias, due to negative potential of the battery is connected to the p-type, majority carriers which are in the p-type are attracted towards to the negative potential, and majority carriers which are called electrons in n side attracted towards to the positive terminal of the battery. Then all those majority carriers are move away from the junction and only minority carriers are cross the junction. So when all majority carriers are move away from the junction means already we have a initial junction, then again due to this reverse voltage, the reverse bias junction will be increases, which is also called depletion width will be increases. So that diode act as a open circuit. In this figure, we can see that how the depletion width increases and it will act as a open circuit. So due to this reverse bias, the junction will be increases. So there will be no charge carriers, majority charge carriers cross the junction. So it will act as an open circuit. likewise. This is the symbol for p-n junction diode. A symbol which represents the arrow and this junction. Simply we can represent this line represents the n-type, this is p-type, and is also called anode, this is called cathode. Now we'll see that characteristic curve, p-n junction diode in reverse bias. If you see this reverse bias region, in the x-axis we'll take a minus VR reverse voltage, and we'll take a y-axis, negative y-axis, we'll take a reverse current minus IR in microampere. Okay, so what happen in reverse bias p-n junction diode? It will act as an open circuit, ideally open circuit, but practically a minority carriers current flow across the junction. So due to this minority carriers, when we are increasing negative voltage, this small fraction of microampere current flow in the p-n junction diode in reverse bias. When we cross this voltage, what happen? The breakdown happen in reverse bias p-n junction diode, then sudden current flow in the p-n junction diode. But don't operate in this breakdown voltage in normal p-n junction diode. Always we operate in this region only. So ideally no current flow in the p-n junction diode in reverse bias, but practically this small current flow which is equal to maybe less than 10 microampere. Now we will see that diode resistances. When we talk about diode resistance, how the diode resistance exists in the p-n junction diode? Whenever in forward bias, which allows the current flow, diode allows the current flow. In reverse bias, it does not allow the current flow. It acts as an open circuit. So definitely there will be a different types of resistance in forward bias and reverse bias. So diode has two types of resistance. One is static resistance, another one is dynamic resistance. What is static resistance? The application of a DC voltage to a circuit containing a semiconductor diode will result in an operating point on the characteristic curve that will not change with time. So now the resistance of a diode at the operating point defined as the ratio of diode voltage to the diode current at that point. Simply, a diode static resistance is nothing but ratio of diode voltage to the diode current at particular point, quietly operating point. This is the exactly characteristic curve to find out the static resistance. Take the VI characteristics in the x-axis VD and y-axis ID, and this is blue color line which represents the characteristic graph for p-n junction diode in forward bias. Take the operating point here, Q point, and the ratio of this corresponding diode voltage to the corresponding diode current is called static resistance. Next, dynamic resistance. It is defined as the ratio of change in diode voltage to the change in diode current. How can we find out this dynamic resistance? Take a straight line drawn tangent to the curve through the Q point as shown in the figure, this figure, and which will define a particular change in voltage and current that can be used to determine ACR dynamic resistance. So this is the blue color dotted line represents the characteristic curve, and take the Q point as a black dot. When we take a straight line drawn through this Q point, a tangent line, and whatever the changes in delta VD of that tangent line slope in x-axis and change in y-axis which can be represented as delta ID. So the ratio of this change in voltage delta VD by delta ID is called dynamic resistance, which is also called slope of reciprocal of slope of this curve. So what is slope actually? Delta y-x by delta x-axis is did by dvd. So it is simply reciprocal of slope dvd by did. So this dynamic resistance can also be derived from diode current equation. Let us see that how to find out the how to derive the dynamic resistance from the diode current equation. So if you see this characteristic curve blue line, the diode current can be written as id is equal to I naught e power Vd by eta Vt minus 1. So this here exponential term which represents the slope of the exponential curve by increasing the voltage after cutting voltage. So by using this diode current equation also we can derive the dynamic resistance. Let us see that how to derive. So id is equal to I naught e power V by Vd by eta Vt minus 1. This can also be write like this, expand the I naught. And this is the differentiation of this equation. For example, this is the equation 1. Differentiation of equation 1 with respect to Vd. Then this equation d by dvd of I naught into e power Vd by eta Vt minus 1 minus I naught. So we know that these two terms differentiation with respect to Vd. In the first term, here it is Vd term. So e power x is differentiation of e power x is nothing but e power x. So take the e power Vd by eta Vt as it is. And then a differentiation of I naught with respect to Vd, which is equal to 0. And then what is the resultant equation is I naught e power Vd by eta Vt. This is e power x and also differentiation with respect to x. So x nothing but here Vd by eta Vt. Here Vd which is equal to 1. So 1 by eta Vt will be there. That resultant 1 by eta Vt. So total expansion I naught by eta Vt e power Vd by eta Vt. This is did by dvd. But what is the dynamic resistance? It is the ratio of differentiation dvd by did. So which is nothing but reciprocal of the above equation. Eta Vt divided by id plus I naught. How can you write id plus I naught? So from this equation, equation 1, if you take the I naught term to the left side, so id plus I naught which is equal to I naught into e power Vd by eta Vt. So whatever this I naught e power Vd by eta Vt which is equal to capital id by capital id plus I naught. So when we take dvd by did is nothing but this is the denominator term comes to the numerator, and this term which is equal to id plus I naught. So totally dvd by did which is equal to dynamic resistance eta Vt by diode current plus reverse saturation current I naught. Since id forward current in PN junction diode is far greater than reverse bias current I naught, so we can neglect I naught, so that the dynamic resistance small rd which is equal to dvd by did is equal to eta Vt by id, where eta is equal to 1 for germanium and eta is equal to 2 for silicon, where Vt is nothing but volt equivalent temperature which is equal to temperature T in Kelvin and divided by 11,600. Here it is T in Kelvin, degree Kelvin. This is about dynamic the resistance in the PN junction diode. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.